Hello and welcome to inControl, the first podcast on control theory. Here we discuss the science of feedback, decision-making, artificial intelligence, and much more. Imagine the pre-dawn sky at a rocket launch site. A slender booster is falling back to Earth, engine flames gimbaling in rapid micro-adjustments to keep it steady. Telemetry beeps cut through the dawn silence as onboard computers sense even the slightest tilt or drift, firing thrusters to correct each one. Moments later, the first stage of this reusable rocket settles onto its landing pad, upright and precise, as if it knew how to land itself. In truth, there's nothing mystical about it. It's the invisible hand of a smart decision-making algorithm guiding every motion. Thrusters throttle down when the booster leans too far, then flare up just in time to stop a tilt. This kind of dramatic landing is a modern marvel, built on a simple principle of control theory. What happens next depends on what just happened. In other words, the rocket is constantly listening to its own behavior and adjusting on the fly. Now imagine you're cruising down the highway. You set your car's cruise control to 100 kilometers per hour. As you ascend the hill, the car automatically revs up, cresting over and coasting downhill. It eases off the throttle. Inside that mundane experience is something almost magical. A machine sensing the world and adjusting its actions accordingly. A simple idea, really. The car's speed feeds back into how much gas the engine gets. Yet this simple idea underlies a profound principle that pervades engineering, nature, and even our social systems. Finally, imagine another scene, half a world away, far from any launchpad or highway. Hundreds of white storks spiral upwards on a thermal column, riding the morning sun's warmth on outstretched wings. As autumn days grow shorter and cooler, subtle hormonal signals, triggered by the changing daylight, have told these birds it's time to migrate. They circle higher and higher, then peel off one by one to glide south along invisible highways of air. Far below, fields and forests respond to the same seasonal cues. As temperatures drop and daylight wanes, sunflowers get the signal to bloom before winter's onset, and deciduous trees shed their leaves. In each case, nature is listening and reacting through environmental feedback. The interplay of light, temperature, and biology that choreographs the cycles of life. Even predator and prey populations follow this kind of oscillating dance. When prey animals are abundant, predator numbers surge. Eventually the predators overhunt, food becomes scarce, and their own population crashes. With fewer hunters around, the prey population rebounds, and the cycle begins anew. From rocket ships to wild ecosystems, feedback loops are everywhere, continuously monitoring conditions and making adjustments to keep complex systems in balance. Welcome back to the inControl Guide to Feedback, where we explore the principles that keep our dynamic world in check. As always, a big shout-out to our main sponsor, NCCR Automation, the National Centre of Competence in research on dependable ubiquitous automation. In our last inControl Guide, we dived into the notions of controllability and observability, how to command a system and know what it's doing. Today, we turn to the heart of it all, feedback. The idea that what you do depends on what happens. Feedback means that actions are based on the results of previous actions, a circular flow of cause and effect. It's a simple notion with profound consequences. Imagine standing barefoot on a shifting paddleboard. As the board tilts, your body instinctively adjusts, flexing your knees, shifting your weight, stretching out your arms, all to stay upright. You don't calculate each single movement consciously. Your brain and muscles are continuously sensing your position, processing that information and making tiny adjustments in real time. That is feedback. It's your body taking account of what just happened, the board's tilt, and using that to influence what you do next. Feedback, in its broadest sense, means taking account of the result of a process and using it to influence the process itself. It's what allows systems, whether biological or mechanical, to respond, adapt, and sometimes even learn. A more playful definition we'll use is, what you do depends on what happens. In engineering terms, a device or algorithm feeds back some of its output or the environment's response into itself as new input, closing the loop. It's the engineered embodiment of what goes around comes around. This can be as literal as a thermostat measuring room temperature and switching the heater on or off, or as abstract as an investor whose buying decisions are swayed by yesterday's stock prices. The essence of feedback is this circular causality. A affects B, and B in turn affects A. But let's not get ahead of ourselves, more on that later. The anatomy of a feedback loop starts with a few key ingredients. It begins with an action, a rocket firing its thrusters, a neuron sending a signal, or a person making a choice. That action produces an outcome, which the system then senses. Maybe onboard sensors detect a slight tilt, neighboring neurons react, or the person observes the consequence of what they just did. Based on that sensed result, the system adjusts. The rocket's computer nudges the thrust, the neuron modulates its firing pattern, the person rethinks their next move. This continuous loop, act, sense, adjust, repeat, can run endlessly. And when tuned well, it allows a system to maintain stability or pursue goals, even as conditions change. A thermostat, for instance, keeps a room near its set point, whether it's snowing or sunny. But when feedback is mistimed or misaligned, the loop can spiral out of control. Like the moment your phone suddenly shrieks with that high-pitched squeal because two people in the same room are on the same call. The microphone picks up its own output from the speaker, re-amplifies it, and the cycle builds rapidly. A runaway loop. For the curious, this phenomenon is known as the Larsen effect. More on that a little later. We'll soon explore the two fundamental flavors of feedback. Negative, which tends to stabilize, and positive, which can amplify and destabilize, and how each shapes the behavior of the systems we build, observe, and inhabit. In everyday terms, we experience feedback loops intuitively. Think about balancing a broom upright on your palm. You watch the broom's tilt and move your hand to compensate, using the broom's position as feedback for your motion. Or consider your home thermostat. It senses the room temperature and turns the furnace on or off, so that if it's too cold, the heat kicks in, and if it's too hot, the furnace shuts off. This basic insight that what you do next should depend on what just happened is the crux of feedback. It's a concept so simple, a child understands it. I push, it moves, so I push less. Yet so deep that it has shaped centuries of technology and thought. In a way, feedback is the universe's way of learning and adapting. It's the mechanism by which systems correct themselves, find balance, or sometimes spiral out of control. It blurs the line between cause and effect. The effect influences the cause in a continuous loop. One famous control textbook notes that straightforward cause and effect reasoning breaks down in a feedback system. The first system influences the second, and the second system influences the first, leading to a circular argument. It is therefore necessary to analyze the system as a whole. In other words, once you close the loop, you can't easily say which part is the doer and which is the done to. They co-create the outcome. Feedback is a dance between an action and its reaction. Today we'll explore how that dance was discovered, refined, and how it plays out in fields from engineering to ecology to AI. Now, although we devoted our very first episode to the prehistory of feedback, tracing it all the way from ancient Alexandria to the dawn of the industrial age, it's worth a brief revisit here, just to see how far back this looping logic goes. Our story doesn't begin with steam engines or control rooms. It begins with water in the 3rd century BC. Ctesibios, a barber turned mechanician in Hellenistic Alexandria, designed what is widely considered the first man-made feedback device, a self-regulating water clock. The idea was elegant. As water flowed into a tank, a float would rise, constricting the inlet valve to keep the flow steady. It's the same principle that governs modern toilet tanks or carburetors. As the level falls, the float opens the valve. As it rises, it closes again. The float and valve create a closed loop. Ctesibios had unknowingly embedded feedback into the fabric of daily life. A millennium and a half later, in the 17th century Europe, a Dutch alchemist named Cornelis Drebbel created what many believe was the world's first thermostat. His goal? To hold a furnace at a constant temperature, not for comfort, but for alchemical experiments to transmute lead into gold. He devised a mercury and alcohol mechanism that would throttle a furnace's air vent based on temperature. As the alcohol expanded, it raised a rod that choked the flame. As it cooled, the flame revived. This early thermostat was so ahead of its time, it eventually found new life in an artificial egg incubator, a feedback loop born of alchemy, and repurposed for farming. And then, finally, we arrive in the age of steam. Not with James Watt inventing the steam engine, that myth doesn't quite hold up, but with Watt refining it, adding a centrifugal governor in the 1780s to stabilize its speed. One of the iconic images of that era is a pair of spinning metal balls mounted on a steam engine. James Watt's flyball governor. The design borrowed from earlier windmill regulators, but Watt and his partner Boulton adapted it for continuous rotary engines. As the engine sped up, spinning metal balls flung outward, choking off steam. As it slowed, they fell inward, opening the valve. Once again, feedback, centrifugal force detecting motion, gravity restoring balance, turned brute force into measured power. The faster the engine tries to run, the more it chokes its own fuel. Negative feedback, slowing itself down. If the engine slows too much, the balls fall inward and the valve opens up, feeding more steam and speeding the engine back up. Watt's governor, patented in 1788, thus kept engines running at a near constant speed without human intervention. It was like the machine had a bit of self-awareness. It converted steam energy into information which controls the machine. The faster you go, the more you throttle back. The slower you go, the more you open up. In effect, Watt gave the steam engine a way to notice its own speed and correct it automatically. Watt's governor was one of the first famous uses of engineered feedback control and became the icon of industrial control. It was so successful that later thinkers, centuries down the line, hailed Watt's governor as an early cybernetic device, a machine with self-regulation. A few years later, physicist James Clerk Maxwell would take these devices from empirical art to theoretical science. In 1868, he published the uber-famous paper on governors, arguably the founding text of control theory. He analyzed stability mathematically and paved the way for formal feedback design. And so through a water thief in Alexandria, an alchemist's oven in Prague, and the roaring boilers of Britain's mills, the idea of feedback took root, as both mechanism and metaphor. This idea of using feedback to stabilize a system didn't stop at steam engines. In the 1920s, feedback had found a new frontier, not in steam or hydraulics, but in electricity, and more specifically, telephony. At the time, the telephone system was undergoing rapid expansion, stringing wires across a continent, but with it came a problem. To carry a conversation over thousands of miles, you needed amplifiers in a chain, lots of them, to boost signals that would otherwise fade into silence. At the time, vacuum tube amplifiers were noisy and prone to distortion. Their amplification gain would drift with temperature, their output varied with age and batch, and when strung together, their imperfections compounded catastrophically. Signals became muffled, jittery, or worse, unintelligible. Bell Labs engineers knew that if telephony was to scale, amplification had to become linear, predictable, and clean. Fast forward to New York City, 1927. A commuter ferry chugs across the Hudson River on a bright August morning. Among the drowsy passengers is 29-year-old Harold Black, a Bell Labs engineer absorbed in thought. Suddenly, inspiration strikes. Let me quote from Black's paper, Inventing the Negative Feedback Amplifier. Then came the morning of Tuesday, August 2nd, 1927, when the concept of the negative feedback amplifier came to me in a flash while I was crossing the Hudson River on the Lackawanna Ferry on my way to work. For more than 50 years, I have pondered how and why the idea came. All I know is that after several years of hard work on the problem, I suddenly realized that if I fed the amplifier output back to the input in reverse phase and kept the device from oscillating, singing as we called it then, I would have exactly what I wanted, a means of cancelling out the distortion in the output. Black has no paper at hand, so he scribbles the idea in the margin of that day's New York Times. By sheer luck, one page is blank and fully dated. On it, he sketches a simple block diagram and equations for his novel Amplifier. 20 minutes later, when the ferry docks, he rushes to the West Street laboratory and grabs a colleague to witness and sign this historic note. His eureka moment is officially on record. To appreciate why Black's ferryboat flash was so revolutionary, we need to rewind a few years. In the 1920s, the telephone industry was pushing to carry multiple calls over extremely long lines. The solution was to use repeater amplifiers along the route to boost fading signals. But the vacuum tube amplifiers of the day were far from perfect. Each added a bit of noise and harmonic distortion. String a dozen amplifiers in tandem, and that distortion multiplied, degrading voice quality very quickly. Early attempts to make so-called super amplifiers had hit a wall. Engineers tried carefully selecting and biasing vacuum tubes and using push-pull circuits with matched tubes to cancel distortion. But, as one Bell Labs expert noted, nothing made a radical improvement. The underlying problem was daunting. Even slight nonlinearity in one amplifier would compound exponentially across many stages. Later, William Doherty of Bell Labs recalled that the task looked almost insoluble because no one knew how to make the amplifiers linear enough. An improvement of hundreds or thousands was needed, not just 10. In short, truly linear amplification over thousands of miles seemed impossible. Harold Black refused to give up. Fresh out of Worcester Polytechnic in 1921, he had joined Western Electric, later renamed Bell Labs, with an eye toward this very challenge. By late 1922, Black was lobbying his bosses to let him focus on the multi-channel amplifier distortion problem. Permission was granted, so long as it didn't interfere with his other assignments, and the young engineer attacked the problem with zeal. He spent nights and weekends studying everything written on nonlinear circuits and modulation theory. Still, progress was slow. By early 1923, after countless failed tweaks, Black was no closer to the 50 decibel distortion reduction they needed. Then came a stroke of inspiration from an unlikely source. On March 16, 1923, Black attended a talk by the legendary Charles Steinmetz at a public lecture in New York. The auditorium was packed. Black had arrived early to snag a front row seat. Steinmetz finally shuffled in, 20 minutes late, clad in blue overalls and short-sleeved work shirt, puffing on the biggest cigar Black had ever seen. The audience erupted in applause at the sight of this eccentric genius. Quoting again from Black's paper, "It was an inspiring lecture. I no longer remember the subject, but I do remember the clarity and logic of his presentation, and how quickly and directly he reached the final conclusion of his talk." That night, Black couldn't sleep. Steinmetz's ability to cut straight to fundamentals sparked an idea. If vacuum tubes themselves could not be made perfectly linear, perhaps one could deal with the distortion directly. In the wee hours of the morning, Black scribbled a bold thought in his notebook. Remove all distortion products from the amplifier output. In other words, take the output of a dirty, distorting amplifier and somehow subtract everything that's not wanted. He imagined splitting the output into two paths. One path would isolate only the distortion, and then cancel that distortion by feeding it back into the amplifier out of phase. The very next day, March 17, 1923, Black sketched out a two-amplifier setup based on this idea, inventing what we now call a feed-forward amplifier. This clever scheme did improve linearity. Black later recalled it, thereby invented the feed-forward amplifier. But it still wasn't enough. The feed-forward design was complex and only cancelled a portion of the distortion, not the complete solution for long-distance telephony. Black's grand dream of an essentially distortionless amplifier remained unfulfilled. By mid-1927, after 6 years of relentless experimentation, Black was still seeking that breakthrough. It's a testament to his determination that he kept at it. And then, on that summer morning ferry ride, it finally all came together. The key insight was strikingly simple and counterintuitive. Instead of attempting to eliminate distortion by adding more elaborate circuitry, Black would allow the amplifier to distort and then correct itself using feedback. He realized he could take a high-gain amplifier and feed a portion of its output back into its input with the phase inverted, effectively subtracting the distortion out. In doing so, the amplifier's excess gain would be spent to linearize the output. Black's notebook sketch from August 2nd, 1927 shows a bare-bones block diagram and two equations, the birth of the negative feedback amplifier. Imagine Black leaning on the ferry rail, eyes gleaming as he finally sees the solution. He knew, of course, that simply connecting an amplifier's output to its input courted disaster, a howl of runaway positive feedback. But Black's genius was to do it in reverse phase, using negative feedback, and with plenty of spare gain to sacrifice. These benefits can be obtained by simply throwing away some gain, utilizing feedback action, he would write later, describing how a 40 decibel excess gain could yield an extraordinary improvement in constancy of amplification and freedom from nonlinearity. Or, as Black summed it up more pithily, negative feedback works by sacrificing gain for higher linearity. In essence, he planned to trade the amplification factor for fidelity, a radical concept in 1927. Back in the lab, Black immediately set about building a prototype of his new idea. There were formidable practical challenges. High-gain vacuum tube amplifiers are finicky. Adding feedback around them can easily lead to high-frequency oscillations, just like a loudspeaker squealing when a microphone feeds back on itself. Sure enough, one early test of Black's circuit broke into a shrill howl. Black and his team called this unwanted self-oscillation singing. A few years later, his colleague Harry Nyquist at Bell Labs would formally derive the criterion to guarantee a feedback loop stays stable and prevent this phenomenon, the famous Nyquist stability criterion. But in 1927, Black had to proceed by intuition and experiment. By December of that year, the payoff was becoming clear. Black demonstrated a single amplifier stage that reduced distortion by a factor of 100,000, a 50 decibel improvement over a broad frequency band. An astonishing level of fidelity that had been pure fantasy a year earlier. The negative feedback amplifier worked. Bell Labs management, initially skeptical, began to rally behind the idea. One director at first insisted Black abandon feedback and just build a super amp using conventional methods, calling the feedback scheme impossible, but was soon proved wrong. In 1930, Bell Labs built 78 feedback amplifier units for a large-scale field trial in Morristown, New Jersey. They strung together 9 feedback amplifiers in tandem, linked by hundreds of miles of cable and repeaters, simulating an unprecedented 7,650-mile telephone connection. The result was nothing short of miraculous. Voices came through loud and clear on the far end. The total loss of the circuit was on the order of 12,000 decibels, yet each feedback amplifier kept the line gain perfectly steady within a decibel or two. And distortion, instead of compounding grotesquely, remained remarkably low. The trial measured overall distortion only a few hundredfold, greater than a single amplifier's, a huge improvement over earlier systems. In Black's words, it was the practical demonstration that stabilized feedback could conquer distance. The reverberations of Black's invention were felt far and wide. When he filed for a patent in 1928, the US Patent Office examiners were so incredulous that they delayed it for 9 years, arguing that such an amplifier, and I quote, would not work. In fact, the British Patent Office flat out treated Black's application to quote Black again in the same manner as one for a perpetual motion machine, refusing to believe the claims. Only after Bell Labs demonstrated dozens of working units did the patents finally issue in 1937. By then, negative feedback amplifiers were already quietly powering phone calls across America. Mervyn Kelly, who later became Bell Labs president, noted that without Black's invention, the present long-distance telephone and television networks would not exist. Once stable negative feedback amplifiers became practical, they revolutionized electronics. An amplifier's behavior no longer depended on the exact vacuum tube characteristics, but largely on the feedback network design. In fact, Black's work was not tied to the technology of its origins. It became a general principle, applicable to transistors, op-amps, you name it. From precision analog circuits to audio oscillators and beyond, the negative feedback loop was a new fundamental tool for engineers. It's no exaggeration when historians say Black's idea is one of the most important breakthroughs in electronics. Around the same time, 1930s, feedback was permeating another field, the science of self-regulating systems. Norbert Wiener, an MIT mathematician, worked on aiming World War II anti-aircraft guns and realized that predicting a moving target was a problem of feedback and control. By 1948, Wiener had synthesized a new discipline he called cybernetics, from the Greek kubernetes, meaning steersman or governor. He defined cybernetics as the study of control and communication in the animal and the machine. Wiener's key realization was that almost all complex processes, biological, mechanical, or social, could be understood as information flowing in loops. Wiener saw feedback everywhere. A thermostat controlling a furnace, that's feedback. A child learning to walk, adjusting each step, feedback. Neurons in our brains firing and then getting adjusted by the results of movement. Feedback. He even worried about feedback in society and machines, warning that if we give too much control to automated systems without understanding the feedback, things could go awry. Quoting from Wiener, "The machine's danger to society is not from the machine itself, but from what man makes of it." Cybernetics launched a whole multidisciplinary wave of research. It inspired economists, biologists, psychologists. Everyone started thinking in terms of feedback loops by the mid-20th century. In earlier episodes, we touched on some of these historical highlights: Watt's governor, Maxwell's stability analysis, the contributions of Nyquist and colleagues at Bell Labs, and Wiener's grand cybernetic vision. Today, those ideas weave into our main theme: understanding the power and limits of feedback. Well, at this point, you might be thinking, hold on, I didn't sign up for a steam-powered stroll through the history of feedback devices. Fair enough, but here's the twist. You're not just hearing about feedback, you are feedback. So is your dog, so is a tree, so is the immune system fighting off a virus in your bloodstream. Let me take you on a quick tour through some of the surprising places feedback shows up. Because once you know what to look for, you start seeing it everywhere. Life itself runs on feedback. Our bodies and the ecosystems around us are a symphony of feedback loops honed by evolution. A familiar example is homeostasis, the processes by which living organisms maintain stable internal conditions. Consider your body temperature. If you overheat, you start sweating to cool down. If you're cold, you shiver to produce heat. This is a classic negative feedback loop. The body senses a deviation from 37 degrees Celsius and triggers responses to counteract that change, keeping you in a narrow range. Countless homeostatic loops operate in you continuously, regulating blood sugar, blood pressure, hydration, and more, each using signals, hormone levels, nerve impulses to detect a condition and adjust bodily functions accordingly. For example, if your blood sugar rises after a meal, your pancreas releases insulin, which causes cells to absorb glucose, lowering blood sugar back toward normal. That's a negative feedback loop in your endocrine system, keeping you stable. Conversely, when a wound heals, platelets release chemicals that attract more platelets. A positive feedback loop piling on cells quickly to form a clot. One of the most dramatic biological examples of feedback is apoptosis, often also dubbed programmed cell death. Apoptosis is a process where a cell essentially commits suicide in a controlled manner. It is crucial for development, like pruning unneeded cells in an embryo, and for preventing cancer. It's triggered through feedback signals. A cell receives either an external death signal from a neighboring cell, for example, immune cells can signal an infected cell to die, or detects internal stress or damage, like DNA damage. These signals activate a cascade of proteins, notably caspases, that amplify their own activation. a positive feedback loop at the molecular scale, leading to the cell's self-destruction. What's striking is how tightly regulated this is. Once the apoptosis feedback loop starts, it's essentially irreversible and quickly goes to completion. Positive feedback ensures a decisive all-or-nothing execution. But the decision to trigger it is gated by many negative feedback checkpoints that keep cells from dying without reason. If those regulatory feedback loops break down, you get diseases. Too little apoptosis can lead to uncontrolled cell growth, that is, cancer. Too much can cause degenerative diseases. Thus, it is a finely tuned balance of feedback loops within a cell that determines life or death outcomes. On a higher level of physiology, consider the brain. When you learn a new skill, say playing piano or riding a bicycle, you do so through trial and error, getting feedback from each attempt. Neurons strengthen some connections and weaken others based on the success or failure of an action. In essence, your brain's ability to learn, plasticity if you wish, is a giant collection of feedback loops. Signals reinforcing those connections that lead to desired outcomes and diminishing those that don't. The system becomes intelligent because it retains memory of what worked and feeds that into future behavior. Feedback is epistemology for organisms. We come to know what works by observing what happened and adapting. Beyond physiology, animal behavior and ecology are full of feedback loops. Predator and prey populations chase each other in cycles. More rabbits means more food for foxes, so the fox population rises. Foxes then eat too many rabbits, so the rabbit population falls, causing foxes to starve and decline, so then rabbits bounce back, and so on. It's a negative feedback oscillation that can stabilize around some equilibrium or sometimes swing wildly if delayed, leading to boom or bust cycles. Another compelling case is migration and animal navigation. Migratory birds, for example, take cues from the environment, day length, photoperiod, temperature changes, food availability, as feedback to decide when to start migrating. As days shorten and the Earth's axial tilt brings autumn, certain neurons in a bird's brain respond to the changing light-dark cycle, triggering migratory restlessness, known by German word for Zugunruhe, and fat accumulation. This is essentially the bird sensing environmental feedback during shorter days and altering its physiology and behavior to migrate. Studies confirm that increasing photoperiod during lengthening days is a primary cue for spring migration in many species, while shorter days signal autumn departures. During migration, birds continuously adjust their flight based on feedback. They correct course if off track, using the sun, stars, or magnetic field as references, and modulate altitude based on air currents. One could say a migrating flock has its own feedback dynamics. Each bird adjusts to its neighbor's positions, avoiding collisions and maintaining the V-formation efficiency. Even in social animals, feedback shapes decisions. Honeybees perform wiggle dances to communicate food sources. The dance duration and vigor give feedback to the hive about where to forage, and other bees follow, which in turn provides feedback to the original dancer. If recruits don't find anything, the dance signal diminishes. In wolf packs or elephant herds, social cues and hierarchies are maintained by feedback signals, like body language and vocalizations. An individual's aggressive action might prompt appeasement signals from others, feeding back to stabilize the social order. And of course, in human society, feedback loops abound. From the way we learn by trial and error with feedback guiding improvement, to economic markets where prices rise, consumers buy less, which feeds back to producers. Social systems are rife with feedback loops, though they can be complex and hard to measure. Consider economics. Market prices are a classic example of a feedback mechanism. If a commodity is scarce, high demand and low supply, its price goes up. That price increase in turn incentivizes producers to make more and consumers to use less, which pushes the price back down towards an equilibrium. As the economists put it, prices tend to fluctuate around the equilibrium. If the price rises too high, it motivates more supply. If too low, increased demand bids the price up. These activities keep the market in balance over time. That's essentially Adam Smith's invisible hand, a negative feedback loop of supply and demand seeking balance. But markets also display positive feedback at times, notably in speculative bubbles. During a stock market bubble, rising stock prices make people optimistic, so more people buy stocks, which pushes prices even higher, attracting even more buyers. This positive feedback loop creates a self-reinforcing cycle, attracting more investors who hope to profit from further price increases. It's a bandwagon effect, feedback that drives instability. Eventually, reality intrudes. The feedback can't inflate value forever, and the bubble pops, often with a feedback-driven crash. Panic selling begets more selling. Societies also have social feedback loops. Ideas or trends can reinforce themselves. If everyone around you repeats the same beliefs, you become more convinced, which in turn encourages you to echo those beliefs louder, persuading others, and so on. In social media, this has given rise to the concept of echo chambers. Algorithms feed us content similar to what we already engage with, creating a feedback loop of affirmation. One commentator described it starkly. Social media platforms work on a devious feedback loop. You see more of everything you agree with and less of everything you disagree with. Over time, your feed becomes an echo of your own views, amplified and insulated from opposing perspectives. This positive feedback fosters polarization. People drift to extremes because any moderate or dissenting feedback is filtered out. We end up with communities that reinforce their own worldview continuously, often to unhealthy degrees. Of course, there can be negative feedback in social systems too. For example, public opinion may swing like a pendulum. If one ideology goes too far, a backlash, negative feedback, restores a balance. But recognizing, and more importantly managing, these feedback loops in society is one of the defining challenges of our time. How we build platforms, what we amplify, which feedbacks we allow to run unchecked. These choices shape our collective behavior. We'll return to that later in the episode. To wrap up this little tour of feedback in the wild, let's turn to something you might not immediately think of as a feedback system. Games. Yes, the kind you play, like video games to board games. Game designers deliberately use feedback loops to shape player experience. Think of an old strategy board game, like Monopoly. Have you ever noticed how sometimes a winning player keeps winning more, rich get richer, while other games give losing players a chance to catch up? Those are feedback loops in game mechanics. A positive feedback loop in a game is often called a snowball effect. Success breeds more success. For instance, in a strategy game like StarCraft, controlling more resources gives you an even bigger army, which lets you capture even more resources, and soon you steamroll the opponent. That can be fun for the winner but frustrating for the loser. On the other hand, negative feedback loops make games more balanced by boosting the underdog or nerfing the leader. A classic example is Mario Kart. The racer in first place gets weaker power-up items, bananas, green shells, while those lagging behind get lightning bolts, stars, and that notorious blue shell. This is a deliberate negative feedback design. It tightens the competition by slowing the leader and giving trailers a chance to catch up. This is exactly how much of modern game design works. Settlers of Catan is a textbook example. It's engineered so that you feel the game stays competitive right up to the final moments. Many sports have informal negative feedback too. Momentum shifts, or the leading team playing more defensively while the trailing team takes more risks. The fun of a game often hinges on tuning these loops. Too much positive feedback and the outcome is decided early. Boring for everyone but the leader. Too much negative feedback, and it might feel like your actions don't matter because the game always evens things out. Designers strive for that sweet spot, where feedback makes the game exciting and skill-based without being discouraging. Stepping back, I hope this short account has made one thing clear. Feedback is everywhere. Engineers didn't invent it. They discovered principles that nature had long employed. Whether it's your body keeping a steady state, a community stabilizing or destabilizing itself, or a game balancing fairness and challenge, feedback loops govern dynamics all around us. They can maintain equilibrium, think of homeostasis and market stability, amplify changes, cascades, bubbles, or drive cycles and oscillations, predator-prey populations, business cycles. The types of feedback, negative, balancing versus positive, reinforcing, tell us whether the loop resists change or accelerates it. And often, complex systems have multiple feedback loops interacting. With that intuition in mind, let's delve a bit into the mathematics and technical concepts that underpin feedback control. Don't worry, we'll keep it gentle and illuminating, even poetic, because the math of feedback is a thing of beauty that explains a lot of what we've been describing. We've thrown around the idea that negative feedback stabilizes and positive feedback amplifies or even destabilizes. That's broadly true. But it's not the whole story. Let's take a moment to ground those terms in real examples and then peek at how engineers and mathematicians formalize stability when intuition alone isn't enough. In nature and technology alike, feedback comes in two flavors: stabilizing, negative, and amplifying, positive. To build intuition, think of a marble in a bowl. A marble settling at the bottom after a bump is a negative feedback effect, while a marble teetering on the inverted bowl edge is a positive feedback effect. Importantly, positive and negative here describe direction, not value. Neither is inherently good or bad. It's context that matters. Across biology, you see both in action. For example, in gene regulatory networks, a positive feedback loop can create a bistable switch, or cellular memory. A gene turns on and stays on, while negative feedback often yields adaptation or rhythms. In fact, circadian clocks, our 24-hour rhythms, are built on delayed negative feedback in gene circuits, and classic predator-prey cycles arise from interlinked feedback between species. Negative feedback broadly opposes change. If a system's output moves in one direction, negative feedback pushes it in the opposite direction, reducing error or deviation. The watt governor and the thermostat are classic examples. If speed or temperature is above target, feedback reduces it. If below, feedback increases it. Negative feedback generally promotes stability, equilibrium, and accuracy. It's the reason you can balance a broom upright on your palm by moving your hand. You move opposite to the lean of the broom. In electronics, Harold Black used negative feedback to reduce distortion. The more the output deviated from the ideal response, the more it was subtracted from the input, flattening nonlinearity. Negative feedback loops damp oscillations and resist change. They are self-correcting, but they do not guarantee stability in all cases. Delays or overly aggressive correction can still produce oscillations or instability. Engineers analyze this with frequency response tools like the Nyquist criterion to ensure feedback is fast and gentle enough to avoid overshoot. In contrast, positive feedback reinforces change. The everyday example is a microphone feeding into a speaker. A tiny sound gets picked up, amplified, recaptured, and amplified again until a screech emerges. Any small deviation is reinforced, leading to runaway growth, a form of instability. Positive feedback can create exponential growth or collapse, often with thresholds. Once you cross a point, the system flips state. In biology, positive feedback drives the rapid upstroke of a neuron's action potential. A bit of depolarization opens ion channels, causing more depolarization until the neuron fires, or the onset of labor. Pressure triggers oxytocin, which triggers more contractions and more pressure until birth. Positive feedback typically pushes a system away from equilibrium, toward a new one or toward saturation. It is tied to instability and phase transitions, which is often exactly the point. Switching in digital circuits, blood clotting, abrupt decisions. So the neat textbook story isn't wrong. Negative feedback is usually stabilizing, error correcting, and positive feedback is destabilizing, error amplifying, at least locally around equilibria. But the real story is richer. Many systems combine both. For instance, an ecosystem might have a negative feedback keeping populations in check most of the time. But if a tipping point is reached, positive feedback kicks in, like a predator population crash leading to a prey overrun. It drives systems away from equilibrium, often toward a new state entirely. Switching circuits use this. Blood clotting uses this. Social networks use this. Markets use this. Life uses this when hesitation is fatal and action must be decisive. Rodolphe Sepulcri calls this the mixed feedback principle, which we discussed in our earlier episode with him. Biological systems don't choose stability or excitability. They layer loops across regimes. At low activity, gentle negative feedback maintains sensitivity. Near a decision boundary, positive feedback kicks in to break symmetry and commit. After the switch, negative feedback returns to regulate. Feedback becomes architecture. A living system must stay stable most of the time, yet depart decisively when needed. Muscles do this, neurons do this, hormone networks do this. It's not either or. When you layer several loops like this, something new appears. Systems can decide at different scales. We talked about this in our episode with Naomi Leonard, and her work captures it beautifully. Imagine a school of fish with no leader. At first, everything is perfectly symmetric. No one fish has a plan, no direction is preferred. Then, a tiny perturbation. Noise, a glint of light, a subtle cue from a neighbor gets amplified. Positive feedback starts to build. One turns, others follow, commitment snowballs. But at the same time, negative feedback keeps the motion coherent and prevents the group from fragmenting. The school turns as one. Bees choosing a nest site show the same dance. So does the human motor system when you decide to move your hand. A quiet stalemate of neural activity breaks. One pattern wins, and action flows. Positive feedback says, act now. Negative feedback says, act together. And out of that tension, real decision emerges. Feedback helps systems decide, to break symmetry, commit, and hold together. But decisions unfold in time. And in feedback systems, time is not just a backdrop. It manifests through a fundamental property called causality. Causality seems simple at first. You press the gas, the car accelerates, input leads, output follows. But once we close the loop, something subtle happens. Cause and effect begin to intertwine, and the very distinction between input and output, even action and reaction, starts to blur. Let's try to unpack that. In many textbooks, we define a dynamical system by how inputs produce outputs over time. That's the input-output view. Clean, directional, causal. But as Jan Willems and many after him have pointed out, this can be deeply misleading. Physical systems don't always come labeled with clear-cut inputs and outputs. They share variables, they interact. A resistor doesn't output current in response to input voltage. It just exists in relation. Assigning input or output roles is often a convenience, not a law of nature. And this becomes even thornier in feedback systems, because feedback loops blur the line between cause and effect. The input affects the output, sure, but the output also shapes the input. The system feeds on itself, and it becomes unclear what is driving what. This is especially true in interconnections, where subsystems mutually influence each other. In those cases, as Jan Willems argued within the framework of his behavioral systems theory, modeling behavior via maps from inputs to outputs becomes inadequate. One needs relations, symmetrical descriptions where time and directionality aren't imposed from the start, and this question becomes even thornier in feedback systems. Once you close the loop, the neat story of input causes output breaks down. The output feeds the input feeds the output, and suddenly the usual direction of causality is fuzzy. What drives what? It's not obvious anymore. This is exactly why Willems pushed us away from the narrow input-output view. In interconnections, cause and effect don't line up in a single direction. The system co-determines itself. A diode is a great example. Try to draw current as a function of voltage, or voltage as a function of current. It doesn't quite work. The relationship is not a function in either direction. It's a constraint, a relation. Same for gears, transformers, transmission lines, heat conduction bars. two-sided devices that don't fit neatly into a single causal arrow. If you insist on an input-output description, you end up with workarounds or awkward transformations. The world doesn't always respect our block diagram conventions. Sometimes the asymmetry isn't just conceptual, it's physical, and this isn't just philosophical musing. Control theory has very concrete examples where the arrow of time reveals itself. One of my favorite examples comes from a beautiful paper by Trifon Gheorghiu and Malcolm Smith titled Feedback Control and the Arrow of Time. Consider a feedback stability problem from everyday life, riding a bicycle. Imagine rolling a bike out of a parking lot. Effortless, right? At reasonable speeds, the dynamics help you stabilize. Otherwise, bicycles wouldn't exist. Now imagine controlling the same bike backward in time, or equivalently, putting the steering at the rear. And suddenly, everything flips. Stabilization becomes nearly impossible in one time direction, yet feasible in the other. On paper, the equations are time-symmetric. Flip the sign on time and the equations don't complain, but the behavior does. As Gheorghiu and Smith explain, stability is intrinsically time-asymmetric. The same differential equation solved backward can describe a system that is wildly unstable. The direction matters. The punchline? In feedback systems, the choice of time axis is itself a modeling assumption, and it shapes how feedback behaves. If we model on a doubly infinite time axis, from minus to plus infinity, many of our neat causal tools break. Systems that are unstable forward in time can look deceptively stable if we allow anti-causal behavior, outputs anticipating inputs. This reveals a central tension in control. The fundamental laws, like Newton's and Maxwell's equations, are time-symmetric, yet our tools for stability, like bounded input, bounded output stability, are in a sense directional. Thus, causality, then, isn't just a mathematical formality. It encodes our asymmetry as observers embedded in time. Bertrand Russell famously dismissed causality as a relic of a bygone age. But in control, we'd say something subtler. Causality is a modeling choice, not a metaphysical truth. And in feedback loops, that choice can hide as much as it reveals. So what's the takeaway? Well, this brings us to a delightful and slightly unsettling idea. Even though the underlying equations of motion are symmetric in time, feedback may not. Stability has an intrinsic direction. Lyapunov tells us a system is stable if trajectories decay as time goes forward. Reverse the video, and those stable trajectories may explode. We don't usually think about this because in practice, we design for the same time arrow we live in. But the asymmetry is real. Control has a psychological arrow of time. We assume the future is where stability must happen, and we never question it. And suddenly, we find ourselves in the neighborhood of thermodynamics and philosophy. In physics, the laws are mostly time-symmetric, but entropy gives us a thermodynamic arrow. In cognition, memory gives us a psychological arrow. In control, feedback gives us another feedback arrow. A resistor obeying the second law looks ordinary forward in time. Flip time, and it becomes a tiny perpetual motion machine. Same with a damper. Passive elements betray time by refusing to run backwards without violating thermodynamics. Likewise, a controller designed to damp motion forward in time becomes an amplifier in reverse. So we arrive at a funny position. Feedback theory, usually so concrete, forces us to think about time, causality, and direction. And the conclusion is subtle. The universe may allow time reversal in principle, but control systems may not, or at least not in a necessarily meaningful way. So if causality gives feedback its direction, uncertainty gives it purpose. So let's get technical, just enough to see the key principles of feedback control. At the heart of any feedback loop is the idea of comparing what is to what should be. In control engineering, we break a feedback system down into 4 key parts. A reference, that's the goal or target value, a sensor, which measures what the system is actually doing, a controller, which figures out how to adjust, and an actuator, which applies that adjustment. But all of this acts on something, and that something is called the plant. The plant is the system being controlled. It could be a car, a robot arm, a power grid, even your body. The feedback loop enables a comparison between what the plant is doing to what it should be doing, and then pushes it closer, one cycle at a time. In other words, the difference between what you want and what you have, the error, is fed into the controller, which pushes the system to reduce that error. This structure is often shown as the classic feedback block diagram. Arrows flowing from the reference to a summing junction, where the output is subtracted, then to the controller, then the plant, and finally looping back via the sensor. Around and around it goes. Compare, compute, act, sense, repeat. Now, once you have that structure in place, reference, controller, plant, sensor, the next question is, how should each part respond? That's where the idea of loop gain comes in, that is the total amplification a signal experiences as it travels around the entire feedback loop. Technically, the loop gain is the product of the gains from each part of the loop, the controller, the plant, and the sensor. And what do we mean by gain? In classical terms, a block's gain tells us how much it amplifies or scales the signal passing through it. A gain of 2 doubles the signal. A gain of 0.5 cuts it in half. Each block in the loop, the controller, the plant, the sensor, has its own gain, and together they multiply to form what's called the loop gain. In a feedback loop, these gains stack, and the overall loop gain determines how aggressively the system responds to errors. One can think of loop gain as how strongly the loop reacts to a deviation. A high loop gain means the controller aggressively corrects even a small error. Low loop gain means it's more sluggish or gentle. Negative feedback with a high loop gain yields very effective error reduction. The system output will closely track the reference. In fact, if loop gain is very large, the closed loop behavior becomes almost independent of the plant's own parameters, and mainly dictated by the feedback network. This was Black's great discovery. By using an amplifier with huge open loop gain and feeding back a portion, the closed loop gain is approximately 1 over beta, where beta is the gain of the component, largely not caring about the exact tube gain. The closed loop system became robust, its performance insensitive to component drift, because the feedback continuously corrects deviations. In general, negative feedback reduces a system's sensitivity to disturbances and parameter changes by roughly a factor of 1 over 1 plus the loop gain. The higher the loop gain, the less any given disturbance or error gets through. This is why feedback is so beloved. It makes systems robust. Your cruise control doesn't need to know the exact incline of the hill or the exact mass of your car. Whatever the disturbance, within reason, feedback will adjust the throttle to maintain speed. But as every engineer learns, there is no free lunch. Crank the loop gain too high and you risk instability. The classic example is chasing your own tail. If you overcorrect a mistake, you might create a new mistake in the opposite direction, leading to oscillation. Remember those early observations that feeding back an amplifier could make it howl or oscillate? Instability in feedback loops usually arises from delay or phase lag in the system. The correction comes too late or overshoots, and the error reverses sign, causing a wild swing. Positive feedback is inherently unstable if unchecked, as it drives values to extremes until something saturates or breaks. But even negative feedback can destabilize if the loop isn't well tuned. For example, Watt's first governors sometimes caused engines to hunt, or, in modern terms, oscillate, if the linkage was too stiff or had delay. It took James Clerk Maxwell's analysis in 1868 to clarify conditions for stability. And later, in the electric age, Harold Nyquist and others developed frequency domain criteria to ensure a feedback loop remained stable, by keeping the loop gain less than 1 at the point where it would reinforce its own lagging oscillations. But there's more to the story than just size. Signals in a feedback loop aren't static, they flow in time. And that's where phase enters. Each block doesn't just scale the signal, it might also delay it, shifting it forward or backward in time. These phase shifts add up as the signal travels through the loop. And if they accumulate the wrong way, they can throw the system off balance. So both gain and phase matter. Together they determine whether the loop gently guides the system toward its goal, or overshoots, oscillates, or even spirals out of control. In control theory, keeping these two in check is the art of making feedback work without letting it backfire. Most control theorists are introduced to feedback control through this clean picture. You've got your plant, your controller, you wrap them in a loop, and you look at the open loop gain. Nice, simple story. Turn the knob, see gain, and phase. Life is good. Except, not quite. Ostrom and Murray, two giants in the field, like to remind us in their book Feedback Systems, an introduction for scientists and engineers, that staring only at that loop transfer doesn't tell the whole story. Two systems can look almost identical in that view and yet behave completely differently once you close the loop. There's a famous cautionary example. A controller cleverly cancels an unstable mode of a plant. On paper, the loop looks tame. In reality, the output explodes with the tiniest nudge. Same loop gain, totally different consequences. That's the first big lesson. Feedback hides subtleties. You can't just look at one transfer curve and call it a day. So, what do we do instead? Control engineers use what Ostrom and Murray call the gang of six. The 6 ways that inputs, disturbances, and noise propagate through a classical feedback interconnection. If you're doing pure feedback, you sometimes see a smaller gang of 4. For LTI systems, these transfer functions fully characterize how the closed-loop system will respond to external stimuli. This isn't new, this is actually going back to the birth of feedback. In the 1930s, Harold Black at Bell Labs figured out that if you feed back the excess gain of an amplifier, suddenly the amplifier stops caring about its own imperfections. Black basically discovered robustness before we called it that, as beautifully summarized by his 1934 quote, "By building an amplifier whose gain is deliberately made, say 40 decibels higher than necessary, and then feeding the output back on the input in such a way as to throw away the excess gain, it has been found possible to effect extraordinary improvement in constancy of amplification and freedom from nonlinearity." This classic insight by Black shows why feedback is so valuable. Huge open-loop gain with feedback yields constant amplification. In modern terms, the feedback loop makes the closed-loop gain insensitive to component variations. As Ostrom and Murray note, Black's idea is that feedback provides robustness to uncertainty, that is, constancy of amplification, enabling control designs based on simplified models. In practice, this means we can design a controller using a nominal model, yet still tolerate parameter changes or neglected dynamics. And of course, Bodie and Nyquist took that insight and made it real engineering practice. They learned the hard way. Yes, high gain can give you beautiful disturbance rejection and model immunity. But push too far and you skate right into instability. Feedback gives, feedback takes. Now, here's where things get really interesting. Robustness isn't just add more gain. Real systems have uncertainties. Friction changes, temperatures drift, loads vary, sensors misbehave, and the true dynamics always have little ghosts hiding in the high frequencies. The whole field of robust control says, don't just tune for the plant you think you have, tune for the family of plants you might have. Design for the unknowns. And this circles back to that subtle point. Two systems might look similar in the open-loop view, but diverge completely when you close the loop. So how does one compare plants in a way that reflects what feedback actually sees? One powerful answer is something called the new gap metric. Think of it like a distance measure between plant behaviors. If two plants are close in this metric, a controller that stabilizes one will probably stabilize the other. If they're far apart, buckle up. So how do engineers design controllers that remain reliable in the face of uncertainty? There isn't one doctrine. Instead, several traditions developed in parallel, each with its own logic. One is the Euler framework. Here, instead of searching for a controller directly, you parameterize all stabilizing controllers with a single stable object, and design becomes the task of selecting that parameter to shape the closed loop. Developed in the 1960s to 70s, it gave a complete parametrization of stabilizing controllers and brought convex structure into feedback design. Another is H-infinity control. which takes a worst-case view of the world. Disturbances are assumed to be as hostile as possible, and the controller is found by solving an optimization problem that guarantees performance even under that adversarial scenario. Emerging in the 1980s, it formalized robustness through energy gain minimization and became the foundation of modern robust synthesis. A third approach is frequency domain loop shaping, typified by quantitative feedback theory. Here the designer works directly on frequency plots, pushing and pulling the loop shape against uncertainty templates to meet performance and robustness goals. Rooted in the 1970s to 80s evolution of classical methods, it extended loop shaping to structured uncertainty through geometric constraints on the Nichols chart. Different methods, different philosophies, but they ultimately converge on the same aim: feedback systems that remain composed, stable, and dependable, even when the environment does not. But here's the philosophical heartbeat of feedback design: you can't have everything. A key part of this design is balancing the so-called sensitivity trade-offs. One usually designs the loop gain so that the sensitivity of the system is low in the frequency range of expected disturbances, but the complementary sensitivity, and thus the control effort, might be high elsewhere. If you push feedback too hard, you might amplify high-frequency noise or create nasty transient responses. This is why control engineers do loop shaping, to get robust performance, read low sensitivity, without inducing oscillations or noise amplification. All this is to say, when you design a feedback loop, you tune how aggressively it reacts. Too tame, and errors persist, so we have poor tracking. Too aggressive, and you overshoot or oscillate, so we have instability and noise. If you smash down sensitivity to disturbances at low frequencies, it will bulge somewhere else. Push here, pain there. This is known as the waterbed effect. Gunther Stein's classic 1989 body lecture, Respect the Unstable, highlights these conservation laws. In particular, plants with unstable poles or high relative degree impose even stricter limits, and unstable pole forces extra peaking in the sensitivity or complementary sensitivity functions. The takeaway is that if plant uncertainty or performance requirements are too severe, no linear feedback can achieve everything simultaneously. In such cases, one may need more advanced solutions, for example, gain-scheduled and adaptive controllers, or nonlinear and multi-loop architectures. Modern control research explores these frontiers, but the classic constraints always apply in the linear setting: speed, robustness, noise, disturbance rejection. Pick your battles. And when you think you've beaten the trade-off, Bodhi's integral taps you on the shoulder and says, "No free lunch." Feedback is powerful, but it doesn't let you cheat physics. Now here's where things get really interesting, because sometimes you don't just want to hold up against uncertainty, which brings us to the idea of adaptation. In this case, you want the system to get better as it runs. You want it to learn. This is where adaptive control enters. Unlike classical feedback, which assumes a fixed controller for a known plant, adaptive control lets the controller learn and adjust itself in real time. It's feedback on top of feedback. So what exactly is adaptation? In classical adaptive control, you assume there's an unknown parameter in the plant, and the controller tries to estimate it online while still stabilizing and regulating the system. As Anu Anaswamy and Miroslav Kirstic emphasized in our past episodes, the magic here is not just learning parameters, it's keeping the system stable while learning. Parameter estimation is only meaningful if the system doesn't crash in the process. Miroslav Kirstic phrases it beautifully in his new book, Robust Adaptive Control, Dead Zone Adapted Disturbance Suppression. The idea that the system is being learned online and that the uncertainty regarding the model would diminish over time with the controller improved as a result holds enormous appeal. Regardless of the challenges encountered, researchers will never stop aspiring to controller improvement in real time using adaptation. The current tide of incorporating machine learning into real-time control is a testament to that. Why do we need feedback for adaptation? Because learning without feedback is guessing. Feedback makes learning grounded in reality. Nature figured this out billions of years ago. Biological systems adapt through feedback loops. From neurons tuning synapses, to organisms adjusting metabolism, to humans learning to ride a bike. In control, adaptation means the controller doesn't stay fixed. It updates itself in real time to cope with unknown or changing dynamics. Change the aircraft weight mid-flight, drop a payload, lose a rotor. Adaptive control senses the mismatch and retunes its gains on the fly. It's feedback on feedback, a meta loop. The key to making adaptive parameter estimates work is closing the loop with feedback. In every adaptive scheme, the parameter update is driven by the tracking error, the difference between the actual output and the reference or model output. Without feedback, the controller would have no data to correct its parameters. By continuously feeding the error back into the adaptation law, the controller is effectively performing real-time system identification. Thus, feedback both regulates the plant and supplies the information needed for learning. Consider the analogy of learning the weight of an object by lifting it. One strategy is feed forward, pick a weight guess and stick with it, which works only if you guessed correctly. A feedback strategy is to try lifting and feel the error, too heavy or too light, then update your estimate. Similarly, an adaptive controller senses how far the output is from the goal and adjusts its gains immediately. This is why closed-loop systems have an edge. In practice, engineers often design the reference inputs or excitation signals, for example, sinusoids and step changes, to ensure persistent excitation while running the closed-loop system, so the adaptation can proceed. The feedback loop keeps all signals bounded and continuously refines the parameter estimates, driving convergence. The theory goes deep. Jakubowicz, in the mid-60s and 70s, showed how adaptive control links to learning via recursive inequalities, developing gradient-like laws that would converge under the right excitation. Narendra and Anaswamy later formalized when parameter learning actually occurs, namely when the system experiences persistent excitation. If the world keeps feeding you diverse enough data, your parameter estimates converge. If not, they may not. But here's the twist. You may still be able to control safely. That's the defining idea of control for learning, not learning for control. And there are real consequences when excitation isn't there. Without enough richness in the data, adaptive systems can experience bursting. Sudden large deviations, brief but dramatic, because the system is updating gains based on thin information. The literature has been meticulous about this. From the early observations in the 70s and 80s to modern high-order tuners that avoid these bursts and ensure uniform asymptotic stability, even in the presence of disturbances. The big point: adaptive control doesn't ask for perfect learning before acting. It acts safely now, learns when it can, and keeps the system within guardrails the whole time. In a way, this brings control and machine learning full circle. Pattern recognition, recursive least squares, adaptive optimal control, different fields, same spirit. Learning is a feedback loop. You try, you fail a little, you adjust, you do better. Backprop in neural nets? It's feedback. How wrong were you? Sent backwards to update parameters. Humans driving a new car? Same thing. You brake too hard, you soften next time. Feedback is how biological and artificial systems improve. And this is where modern control and modern AI meet. Safe learning under uncertainty in real time on real systems that must not fail. Control people have been here for decades, proving what's safe, what converges, what must be bounded, what cannot be violated. Machine learning brings huge expressive power. Adaptive control brings guarantees and humility in the face of the unknown. Together, they form a compelling vision. Systems that not only hold up under uncertainty, but learn their way toward better behavior without ever crossing safety lines. It's a vision where systems remain safe as they learn, adapt, and self-improve. And that vision is precisely where control theory meets modern AI, in the quiet power of feedback. Modern manifestations, AI in the loop, media, and misalignment. In the era of AI and complex networks, feedback loops are more relevant and visible than ever. consider reinforcement learning, one of the most visible branches of AI these days. In RL, an agent, like a software player playing a game or a robot learning to walk, takes actions and gets feedback in the form of rewards or penalties. This feedback is then used to update the agent's policy, so it will take better actions in the future. It's essentially trial and error, guided by a feedback signal. The agent tries something, the environment rewards it if that is good, or punishes if not. And the agent adjusts its behavior accordingly. This is fundamentally a closed-loop learning process. When DeepMind's AlphaGo learned to play Go at superhuman level, it did so by playing millions of games against itself, each move leading to a win or loss, feeding back into its network to update move preferences. In control contexts, we now see deep reinforcement learning controlling robots, industrial processes, even autonomous vehicles. These AI controllers don't follow a fixed equation we designed. They learn the control policy by optimizing feedback over time. It's powerful, but it introduces new challenges, like how to ensure the learned feedback policy is stable and safe in all situations, a hot research topic. Another modern feedback loop we all interact with daily is the social media news recommendation algorithm. We touched on echo chambers earlier. Let's unpack the mechanism. Platforms like YouTube, Facebook, Twitter, TikTok have algorithms that observe what you click, watch, like, or share. That's feedback from you to the system about what you find engaging. The algorithms then adjust what they show you next, typically giving you more of the same or content that similar users found engaging. This creates a loop. Your behavior influences your future information diet. Over time, you effectively hand-curate your own feed by reinforcing certain types of content. The algorithm's goal is usually to maximize your engagement, so they show you things you're likely to click on based on the feedback of your past clicks. This loop can lead to filter bubbles or rabbit holes, where you might start with one video on, say, healthy eating, and end up being fed extreme diet conspiracy videos, because each step of the feedback loop pushes you a bit further in the direction of what kept you hooked. As one writer succinctly said, you see more of everything you agree with and less of everything you disagree with, which creates and reinforces echo chambers that algorithmically amplify content matching our existing biases. A destructive feedback loop. The positive feedback here is between content and confirmation bias. The more you engage with the type of content, the more the system gives it to you, which increases your belief or interest in that content, making you engage with it even more. We've seen how this can fuel polarization, misinformation, even radicalization. It's literally feedback run amok in the social sphere. The platform designs didn't set out to polarize, they simply optimized for engagement. But that objective plugged into a human social system with our psychology resulted in unintended self-reinforcing spirals. Now, there's a lot of effort to insert negative feedback or dampening into these systems. For example, mixing in diverse content or prompts like, "Are you sure you want to share this article? You haven't opened it." Essentially friction to break the loop. It's a vivid example that understanding feedback is not just academic, it's shaping democracies and public health. Think of feedback loops of vaccine misinformation, etc. And finally, one of the most profound and speculative feedback discussions today: AI alignment and runaway feedback. This is almost like science fiction, but serious people are concerned about it. The scenario often given is something like the paperclip maximizer thought experiment. Imagine a highly advanced AI is given a simple goal: manufacture as many paperclips as possible. It has the ability to act in the world, improve itself, and acquire resources, a highly capable feedback-driven agent. Without proper checks, this AI might start converting everything, including human infrastructure, including you and me, into paperclip-making material, because that increases its reward. If humans try to turn it off, that's seen as a threat to paperclip production, so the AI might even resist or eliminate the interference. Absurd as it sounds, it's a parable. A powerful feedback optimizer with an ill-specified goal can theoretically feedback on itself to become more and more extreme. It's essentially positive feedback on its own goal pursuit, an exponential runaway. Now, in real life, we are far from that scenario, but we do see glimpses. AI algorithms in finance have caused flash crashes by feedbacking on each other's actions. One algorithm sells, dropping the price, triggering another to sell faster, and within minutes the market freefalls until circuit breakers intervene. A positive feedback loop in algorithmic trading. Or consider simpler AI glitches, a content recommendation AI that learns to maximize engagement might discover that outrage or extreme content keeps eyes glued to the screen, and thus it starts filling feeds with extreme stuff. Not because anyone explicitly told it to polarize people, but because its feedback loop engagement led it there. This is essentially an uncontrolled feedback escalation. The field of AI alignment grapples with guiding these powerful feedback-driven systems in ways that remain under control and in line with human values. How do we embed negative feedback, checks and balances into a super-intelligent agent so that if it starts to go off the rails, it self-corrects or allows us to correct it? Norbert Wiener presciently warned in 1948 that once machines start making decisions, we must limit the feedback authority we give them. Intelligent machines might not always make decisions in ways humans would foresee or want. The machine's danger is not the machine itself, but in how we use it, he said, advising that we keep a feedback leash on automation. In essence, don't let the loop run unfettered. Today, techniques like reinforcement learning from human feedback, RLHF, are used to align AI models. For example, ChatGPT was trained in part by humans providing feedback on its outputs to fine-tune it. That's a meta-feedback process aiming to incorporate our values. It's promising, but not foolproof. It's like raising a child by feedback. You can guide them, but there's no guarantee they won't find a loophole in your guidance if they become extremely capable. So the conversation continues. How to design feedback loops in AI and in socio-technical systems that amplify the good and dampen the bad. We've now spanned from Watt's mechanical regulator to self-learning algorithms and global networks. What a journey of feedback in action. To wrap up, let's step back and reflect philosophically on what feedback means for how we understand and control our world. There's a deep philosophical truth in feedback. It is how systems know and change. In epistemology, the theory of knowledge, one might say we only truly know something by observing the results of our interactions with it. A scientist forms a hypothesis, conducts an experiment, gets feedback from nature, data, and updates the hypothesis. That's a feedback loop of learning. Similarly, a child touches a hot stove, gets burned, feedback, and updates their understanding, hot things hurt. Feedback underlies learning by doing, a concept philosophers from John Dewey to Karl Popper have emphasized. Trial and error, conjecture and refutation, all are feedback processes. In a very real sense, feedback seems to be the universe's way of processing information. Every feedback loop is a little story of error and correction, or reinforcement and change. The system and its environment engage in a dialogue. In the age of AI and autonomous systems, understanding this dialogue is more crucial than ever. It's related to how we align machines with our goals, by constantly checking and adjusting how we adjust in meta-feedback. It's how we avoid the pitfalls of uncontrolled loops, be it a social media algorithm or a climate tipping point, by identifying runaway positive feedbacks and countering them with negative feedback interventions. It's also how we, as individuals, grow. We reflect on our actions, feeding back outcomes into our decisions, and we change course as needed. As we conclude this guide to feedback, if this episode worked, you'll now start noticing feedback in places you previously ignored. If it didn't, well, that's also feedback. Thank you for listening to the inControl Guide to Feedback. I hope this episode fed your curiosity and will help guide your understanding of all feedback loops that weave through our world. Until next time, stay in control and stay open to feedback.
Thank you for listening. I hope you liked the show today. If you enjoyed the podcast,
please consider giving us 5 stars on Apple Podcasts, follow us on Spotify, support on Patreon or PayPal, and connect with us on social media platforms. See you next time!